The subject of amber in the post lecture should not come as a surprise, as there are significant deposits of this raw material in our country and the Baltic states. And there is no need to convince anyone that amber is worth of attention of archaeologists. Today's lecture will be a kind of introduction to the issue of amber in archaeology. I will tell you about what is worth knowing at the beginning, and this will be very diverse matters. First, I will devote a few words to the name of amber in selected languages. Then I will discuss the issue of amber geology, its physical properties and varieties. Next, I will deal with the topic of the location of amber deposits in the world, mainly in Europe, in order to proceed to a review of most important contemporary physical methods of amber research. Another topic will be issue of amber aging, which is worth spending a few moments on. The last part concerns the place of amber in the culture of the oldest European societies. I will outline the process of amber spreading across the continent, and finally recall one of the Greek myths that answer the question, how was amber formed? So, as you can see, a bit of everything. As far as the names of amber in Latin, amber was called succinite. Some texts also use a Latinized Germanic term, glassum. In modern languages, the most popular terms are amber in English, lambre in French, and lambra in Italian. Among the Slavonic languages, the form jantar prevails. However, in Serbian, amber is called cilibar. The Polish name, bursztyn, derives from the German term der Bernstein, which refers to one of the properties of this material and translates literally burning stone. In ancient Greek, it is called elektros or electron, and in modern Greek, elektro or kehibari, differing from Turkish and Persian. Elektro is a more scholarly use, and kehibari more common usage. The discipline of science that deal with amber first was geology, because amber is a mineral like stones on rocks. However, it is a specific mineral of organic origin, such as hard coal, for example. Amber belongs to the category of fossil resins. In order for the resin of living trees in amber forests to acquire fossil properties, it must be transferred from the biosphere to the geosphere. The first stage, that is volatilization of the volatile components of the resin, took place immediately after contact with air, while still on the tree. Nevertheless, the most important active factor in this process were the rivers over which amber forests grow. The waters of those rivers carried with the current the trunks of trees originally growing on the banks with the concentrated leaks of resins and stored them in the deltas. Thus, the resin concentrations got into the geological structures. There, under the influence of time, pressure, and retention condition, like constant temperature, no air access, the process of transformation of the resin into a fossil resin took place. The formation of fossil resins was not related to one geological period. They were created in different stages of the history of the Earth. What is more, they are still being created today. The oldest of them are dated to Devonian, from approximately 420 to 360 million years ago. And the youngest, called copals, are still have approximately 10,000 years. The most active geological period in terms of the genesis of fossil resins was the Upper Eocene, so 40 million years ago, when succinite, one of the most widespread fossil resin, was formed in contemporary Central and Eastern Europe. The physical properties of the fossil resins are specific. They are light. The density is on average 1.056 grams per cubic centimeter, although there are varieties, so-called firm amber, with a density of about 0.350 grams per cubic centimeter. For example, gold has a density of 19.3 grams per cubic centimeter, so it is 20 times heavier than amber. At the temperature of 125 to 200 centigrade, amber softens. At the temperature of 330 to 380 centigrade, becomes a liquid, and it decomposes, so burns, at the temperature of 370, 380 centigrades. At the same time, it gives off an aromatic skin of incense. It is often a component of incense. Amber is a very soft material. The succinite micro hardness coefficient is approximately 270, 250 MPa. Amber is also a magnetic material. After rubbing, it attracts particles of matter. Amber is very diverse in terms of color and degree of transparency. It depends on the type of and the degree of impurities and the oxidation stage. Of the dozens of its varieties, two are the most common. Pure amber without impurities and non-oxidized. It is transparent and has a honey color, as you can see on the left side. And then opaque, milk white amber, which is uniformly opaque due to macroscopic air bubbles. Moreover, amber can be contaminated with minerals like pyrite color, blue, gray, black, combination with earth, or with organic substances. The decomposition turns amber into olive, green, or brown color. Individual amber concretions are often characterized by a few kinds of color because different varieties can be combined in one lamp. The sticky resin was also a trap for small animals, but also many of them survived in amber to our times. Amber is therefore a kind of time capsule. for many animals that lived in amber forests, especially for insects. There are exceptional finds, such as this lizard shown in the slide, embodied in amber, which is 40 million years old. The field of zoology, entomology, owns amber hundreds or thousands of newly designated species of insects. Let's summarize this stage of our lecture. Amber is a mineral like stone, but strongly paradoxical. It is light stone. It feels warm to the touch. It is a warm stone. It is a flammable stone. It is a stone of many colors, kind of mineral chameleon. It is stone with varying degrees of transparency. It is soft stone, and it is also magnetic stone. You might think it is easy to process. Nothing could be more wrong. Although it is soft, it also has a heterogeneous internal structure. Also with internal cracks. For example, drilling a hole in such a raw material for an inexperienced manufacturer usually results in the disintegration of lump, thus a waste of time and raw material. Deposits of fossil resins are known all over the world and are found on all continents except Antarctica. They are most dense in Europe, probably because it is the most studied continent in this respect. Interestingly, one of the few parts of Europe where deposits of fossil resins have not been discovered so far is Aegean. This fact facilitates research on prehistoric and ancient amber products that we found in Greece. We are sure that they are all imports. The largest amber deposits in Europe are made of succinite. They are located in Central Europe and have already been known and used since time immemorial. Methods of separating varieties, so taxonomy of fossil resins, in the beginning were based on geology. The deposits of fossil resins discovered by geologists received their local names, which we saw on presented maps. This allowed for determination of two basic parameters: time, geological origin, and place, geographical location. This process has been going on since the end of the 18th century and resulted with a wealth of names for local fossil resins. In the course of the 19th century, research began on the physicochemical properties of fossil resins. At that time, the first differences in the composition and structure of individual varieties were discovered. Much attention was paid to the absence of or presence of the succinite acid and the percentage of each contained in the chemical composition of the given variety. It was already clear then that in Europe, the Baltic amber variety, so succinite, was a key importance, but other varieties were also distinguished. In the Mediterranean zone, the so-called Sicilian amber, symmetry, was most important. The achievements of scientists until the middle 20th century showed the complex chemical structure of fossil resins, which is characteristic of organic bodies. Moreover, it can be said that the chemical structure is non-standardized. There are particularly no identical amber nuggets, unlike minerals such as diamonds, where each concrete has the same structure. The progress that has taken place, especially in the 20th century, in the field of methodology of physical and chemical research, has become the base of hope that the goal of unambitious, so objective systematics of fossil resin will be successful. In this regard, archaeologists also joined the group of scientists who are interested in it. The postulated objective systematics of fossil resins could be a very useful tool in the study of cultural role of amber. The goal was as follows: to find an analytical method, preferably a non-invasive one, and on which the device will be built. All you need to do is insert the artifact under study into the device, and the display will inform you that it is the X variety of fossil resin, the deposits of which are located in the Y region. Very easy to say, isn't it? Let's see by what ways this intention was attempted. What is the palette of the most popular methods for testing fossil resins? I mention a few of them. Among the chromatographic methods, gas chromatography coupled with mass spectrometry is the most effective method of studying the molecular structure of fossil resins. Thermal analysis methods, measurement of energy effects, as well as the size of mass loss in various temperature ranges was used. As a destructive method, it has little use in archaeology. The largest group are spectroscopic methods. X-ray spectrometry reveals the amorphous nature, so non-crystalline structure of fossil resins. It allows us to distinguish them from all types of crystalline minerals. Nuclear magnetic resonance spectroscopy provide information on the molecular and macromolecular structure of amber. Electron parametric resonance spectroscopy is used to obtain information on the formation of free radicals in amber, which may indicate aging changes, including post-depositing changes like heating, roasting, oxidation, grinding, pressing, and so on. For an example, honey transparent amber that is well preserved has 10 times less free radicals than dark, so old amber, respectively, 10 to the 14 power and 10 to the 15 power spins per gram. Ultraviolet spectroscopy is important in comparative analysis of resins of different ages and origins. Fourier transform infrared spectrometry is the most widely used method of studying fossil resins, especially useful for the separation of succinite. It is also possible to isolate cematite. It was introduced to amber research in the 1960s in the USA, Germany, and the Soviet Union simultaneously. The key role in the application of this method to archaeology was played by Professor Kurt Beck of Vassar College, USA. Among other things, he and his team examined the largest collection of amber items from the Mycenaean culture. How can we summarize the experience so far? The phase of experiments and searches is still ongoing. We do not have a method that can be the base of an objective systematics of fossil resins. Moreover, it is becoming more and more common to think that such a method does not exist due to the nature of the fossil resins. In one deposit of fossil resins, for instance, in the southern Baltic Sea, they are usually more than one variety. This may be due to the fact that there were several species of resinous trees in the amber forest. Fortunately, there are still scientists who do not give up hope. An example is colleagues from Czech Republic, Dr. Kulcha and Dr. Bednář, who recently undertook the task of clearly linking the places of origin of individual amber artifacts brought to the territory of the Czech Republic 4,000 years ago with specific places within the South Baltic deposits. They use laser desorption, ionization, high-resolution tandem mass spectrometry. Oof, it's not so easy for the not scientist like me. Related to multivariate statistic, so principal components analysis. The first results seem promising, but only a few analyses have been made, which is not a sufficient base for comprehensive evaluation of the method's effectiveness. However, this part of our consideration can also be summed up with an optimistic accent. Thanks to the FTIR method, we are able to recognize succinite among the fossil resins, which is the main component of Baltic deposits. A specific fingerprint of succinite on the spectroscopic diagram is the so-called Baltic shoulder, which you can see on the slide. This method also makes it possible to distinguish the fossil resin of the largest deposits in the Mediterranean zone, namely cementite organic in Sicily. FTIR analysis performed for fossil resins artifacts related to the Mycenaean culture clearly indicate that the vast majority of it was succinite. Therefore, in the following section of a lecture, I will prefer this type of fossil resins. Another complication in the archaeometry of prehistoric fossil resins is the phenomenon of aging of amber mentioned above. As you remember, the geological environment of the formation of fossil resins was characterized by high pressure, stable temperature, and lack of oxygen. Nevertheless, a very important feature of succinite deposits is the secondary nature of many of them. The glacier, which covered the entire northern and central part of Europe after the succinite formation period, played a crucial role in this process. Part of the original deposits in the deltas of the upper Eocene rivers were displaced by the ice sheet, and most importantly, this changed the condition of the deposition of these deposits, fragmenting lumps, exposing them to an in changeable temperature conditions, and contact with oxygen, which in many cases triggered the aging process of amber. What was it about? I have already mentioned above about the increase in the proportion of free radicals. In general, those were the process of oxidation of many compounds that make up the fossil resin. The result of these processes was a changing in the physical properties of given concretion. The dynamics of oxidation process is related to various factors, especially accessibility, temperature, humidity, and exposition to light. The crucial factor is the accessibility of iron that contains oxygen. Dynamic changes of temperature and humidity accelerate the chemical degradation of amber. Moreover, exposure of an artifact to sunlight also results in faster degradation. How does the aging of amber occur? It involves the change of its physical properties. For archaeological research, most important ones are color, transparency, and structure. The most common kind of amber, the transparent honey yellow, after several dozen years become darkened and afterwards change in the color of ruby after a few hundred years. Later, cracks appear on its surface and subsequently penetrate inside the artifact. This results in the loss of transparency and color. The item becomes brown with its structure resembling brown sugar. Opaque milk-white specimens change the color to dark yellow or a little brown during the first few decades. Afterward, they become darkened and more intensive in color, only to change into ruby finally as well. Later, similarly to the first kind, the surface cracks, which results in almost total degradation of the artifact. In the case of those two kinds, we witness the same final phase of degradation. The process of aging of amber takes place for natural reasons such as the formation of secondary deposits due to activity of the glacier. The second, for researchers of the culture role of amber, much more important cause of amber aging is man, as a user of amber artifacts. Nevertheless, there was also one factor that could slow down the aging processes. Processed amber with polished surfaces is more resistant to the aging processes. This factor worked since the moment each amber artifact appeared in the Aegean. What is mean? There is the assumption widely accepted in the scholarship that amber objects reached the Aegean as already crafted items with a well-polished surface. It replaced a natural porous surface, and they may effectively block the aging of amber. Nevertheless, from the Aegean perspective, the remaining natural factors, especially the climate, so temperature and humidity, were the stable factor that resulted in the acceleration of aging processes. A similar effect was caused by a specific way of amber artifacts were used in the Mycenaean culture. The basic function was to decorate the body and dress of members of the elites during official feasting, cult events, receiving guests, or taking visitations. Those amber objects certainly were often exposed on the sunlight. The post-deposit stage is of equal importance to the aging process of amber artifacts. Those items were deposited in graves or deposits or lost in settlements. This consistently exposed them to factors accelerating oxidation. This fact is of great importance for the recognition of amber artifacts during excavation. Old amber does not differ much from the lumps of brown-gray earth. It also succumbs to the exploration tool used during the excavation without too much resistance. We can simply scrape such an artifact with a spatula without recognizing what just happened. Therefore, explorers need to know what an amber artifact in the culture layer may look like. There are also known methods of conservation degraded amber finds in situ, but that is maybe a different topic of different lecture. This is how we move step by step to more culture analysis of amber. I will now outline the dynamics of the spread of succinite in Europe. Man's first encounter with amber took place on the beaches or by the rivers, where the concretions washed out by the water line. The beginnings of contact with amber were therefore similar to those in the case of metal nuggets, mainly gold. We date the oldest amber artifacts to the Palaeolithic, but there are very few of them. In Europe, only the sliding north of the ice sheet made it possible in the next epoch, in Mesolithic, to settle amber-bearing areas on the Baltic Sea. It was approximately 10,000 years BC. The oldest inhabitants of those lands, following the melting glacier, immediately become interested in them. Amber became an intensive processed raw material. In the Mesolithic, the future production of amber was especially rich. Those traditions were continued by farmers who came to the Baltic Sea at the turn of 5th and 4th millennium BC. The model of amber use that was in force at that time was characterized by locality. It focused on amber-bearing areas only, and the wealth of production of body ornaments and custom ornaments, as well as anthropo and zoomorphic objects. We also know production workshops from those times, thanks to which we have detailed information about the technological knowledge of manufacturers of that time. In the first half of the 3rd millennium BC, amber use noticeably spread southeast as far as Volhynian and Podolian as a result of processes taking place in global amphora culture. In the second half of the 3rd millennium BC, the area of succinite adaptation extended to include most of Central Europe, mainly the territory of present-day Germany and the British Islands. More importantly, in that period, the raw material reached the Mediterranean for the first time, which can be seen in the finds from southern France, west of the Alps, which is the research of Colette Dugardin, who is with us this night. This was possible because amber goods were included in the network of long-distance exchange organized by the bell-beaker communities in Western and Central Europe. It is already then when a twofold character of amber dispersion manifests itself. Although amber is found throughout the entire described area, it is possible to identify regions with a higher concentration of finds. In the second half of the third millennium BC, the latter was still the Baltic coast area due to its amber-bearing character. A clear watershed in amber dispersion is the year around 2000 BC, after which the raw material came to be known in large amount over considerable larger expanses of our continent, which included the British Island. More thinly dispersed succinite artifacts are known from the Bohemia Basin, Carpathian Basin, the Caput Area region, throughout Western Europe as far as the Iberian Peninsula. At that time, however, the intensity of amber use saw a decrease in today's Eastern Poland and Western Ukraine. After 1800 BC, amber was universally known raw material throughout Europe. At that time, too, mainly between 1800 and 1600 BC, a major change took place in the distribution of principal amber artifacts concentration on the map of our continent. They no longer coincided with the amber-bearing areas of Northern Europe. This was especially the case of the Baltic. Most amber goods are recorded then in the Bohemian Basin and more broadly across the whole ecumen of the Unitice culture, and in Carpathian Basin and in the British Islands and also in Aegean, with the inception of the Mycenaean culture. This fact may be considered a sign of a new culture economic status reached by amber, especially in the Mediterranean among civilized societies as raw material used by elites. Around the middle of the second millennium BC, in the picture outlined above, a single but notable change took place. It involved, on the one hand, a marked decline of amber finds on the British Island, and on the other, a stronger amber presence in the upper Rhine and Danube, that is in the region where the tumulus culture rapidly grew. Another important watershed is the growth of amber dispersion, in particular in the Mediterranean, falls in the years after 1200 BC, that is, at the end of the second and the beginning of the first millennium BC. This period witnessed a weakening of presence of amber in Aegean, accompanied by its rise in Apennine Peninsula. The central Mediterranean has been the main destination of northern succinite since then. During the first half of the first millennium BC, the area with a highest concentration of amber finds was the Caput Adria region, which contains of the North Adriatic area, that is northern and middle Italy and western Balkans. In the later stages of prehistory, since the second half of the 3rd millennium BC and at the various stages of the later, amber was intensively exchanged across the entire continent, but it was Italy and later Rome that became principal consumer of amber for many centuries. In the case of Mediterranean Messenian cultures, we observe an extraordinary level of amber use. So from the around 1800 BC to 1100 to 1000 BC, so almost 800 years, which takes place, let us emphasize it strongly, within one continuous culture tradition. Undoubtedly, the presence of amber in Greek mythology was a reflection of this long-lasting symbiosis. Also, myths related to genesis of amber. I will quote one of its versions. It is about Phaethon. He was the son of the sun god Helios. Once, Phaethon asked his father to let him drive for one only time the sun chariot on which the sun made its daily journey throughout the sky. Father reluctantly but agreed. Phaethon, as befits young daredevils, had no experience in successfully driving a team. The horses sensed it, and instead of the daily straight path, the sun began to dance in the sky, moving away from the earth or approaching its surface dangerously again. Especially the latter was extremely dangerous for life on earth because the fireball of sun burned out everything what was alive. So they were cries for rescue, which reached Zeus in his palace on Olympus. And Zeus struck down the daredevil, who fell into the river flowing somewhere in the north, of course from the Greek point of view, associated with Po River in northern Italy. Phaethon's sisters, known as the Heliads, and his friend Kykenos mourned his fate on the river, and they trees turned to amber. They were changed by gods, respectively, Heliads into purples and Kykenos into swan. This myth is simply a mine of meanings. Nothing is accidental here. Amber in the context of the sun, trees and river, north and swan. But that is completely different story. So thank you for your attention. Merci beaucoup for the attention.